This is WBCQ, bringing World's Last Chance Radio to you from Monticello, Maine, USA.
WBCQ, Monticello, Maine, USA.
With 500,000 watts out, this tube rig rocks.
Type 176 tetrode, which is an output tube, costs $210,000.
Troubleshooting complex solutions for advanced technical problems.
The fix for that was masking tape.
A transmitter made by Continental in USA.
Continental builds great equipment.
The superstation WBCQ is Northern Maine's 20 million watt shortwave powerhouse for the world. A little over 4 years ago, World's Last Chance Ministry teamed up with Monticello shortwave radio station owners Allan and Angela Weiner to create the most powerful radio station in Maine, and perhaps New England. World's Last Chance bills itself as a non-denominational church that has become dissatisfied with the watered-down truths preached in establishment churches today. World's Last Chance Radio is developing a series of end-time messages that will be broadcast worldwide in 10 languages over shortwave radio from WBCQ.
We're a Ma and Pa organization. Here's Ma, co-owner of all of this madness. And our goal is free speech radio. And our client, World's Last Chance Ministries, which are wonderful, beautiful people. They are just the most pleasant people on earth. They are God-fearing. They love our Lord and Savior. They're wonderful, wonderful people. They came to us because WBCQ has the reputation of being the foremost free speech radio station in the world. That's why they came to us. And they said, we want to be on your transmitters. And I said, fine, we'll put you on our transmitters. And they said, well, how much power are you? So we're 50,000 watts at the classic site. And they said, well, that's not enough. We need more. I said, well, we don't have more. I said, well, build more. I said, well, fine, we can do it, but it's going to cost millions of dollars. And they said, fine. So so we got into a pretty informal arrangement where they sponsored and provided the financing for WBCQ to expand and build what we call affectionately transmitter and antenna number 6. And we built it, and all on the foundation of freedom of speech, freedom of religion, and it's been a wonderful relationship, and they've been doing, God's good work, and here we are today, and I think it's vital because, well, the cancel culture, everything that's going on now, freedom of speech is at jeopardy, and the superstation, we feel, is a world asset, because other nations are tearing down, shortwave stations left and right.
Construction for the new radio station began at the Weiners' long-standing location on Britain Road, on the outskirts of the small-town community of Monticello in northern Maine. The most visible sign of WBCQ is its massive antenna array, towering above the treetops. Since nobody is building large-scale rotatable antenna arrays with variable beam width patterns in the U.S., the Weiners had to look to Europe for the solution.
Well, it's the antenna itself, I guess you would say the brains in the antenna.
Yeah. That is so.
Germany.
Yeah. Everything was fabricated in Germany and Switzerland, and was shipped over here from Germany and parts from Switzerland. Some of the steel parts were fabricated, believe it or not, in China, and they were shipped from, I think, Hong Kong and Singapore. So the antenna is very international. It has components from companies all over the world. The electronics in it are primarily from, Siemens?
Yeah, in Italy.
In Italy. And some other controllers are from other European nations. So it's really an antenna of international proportions. It's a massive computer structure. There are motor controllers. There are digital sensors that monitor certain parts of the antenna that are water cooled. There's a section of the antenna called the tubular section, which comprises about 100 feet from the base up to a superstructure that goes another 120, 130 feet up. And in that tubular section is all kinds of massive switching, and there's the antenna tuning unit, which matches the 500,000 watts from the transmitter to the various dipole antenna bays.
The antenna mast at WBCQ is 260 feet high and weighs 400,000 pounds. For an antenna of this size, it was an engineering miracle to design the tower to be fully rotatable through 360 degrees and allow for instantaneous adjustment of the radiation pattern of the RF energy from wide to very narrow, similar to an adjustable beam flashlight.
Because the antenna is actually made up of 16 dipoles that are switchable in all different kinds of configurations. It's kind of like a radio searchlight is the best way to describe the great antenna that we have here, built by Ampagon in Switzerland. It can be like a flashlight that has a controllable beam. We can do the same thing with that antenna. We can set the dipoles at various configurations to make the beam like fat this way, narrow this way, or fat this way, narrow that way. And that helps us get into just about any country on Earth, depending on where we're pointing it. All the dipoles act as the radiating element. The reflector is a huge copper screen that is mounted behind the dipoles. It's actually known as a curtain antenna because it has a curtain of wires, copper wires, thick copper wires, behind the dipoles that give it directionality.
The antenna array is actually a dual-band configuration with a matrix of dipoles on either side of the copper screen curtain that are designed for different portions of the shortwave bands.
If you look at the antenna, you look at photographs, you'll see that there are these big white dipoles which center around 9 megahertz, even though they're tunable from 5 to about 12 megahertz. Then there's another set of dipoles, another 16 dipoles. They're smaller. They're on the back, and they go from about 15 to 30 megahertz. So depending on the band of frequencies that we want to use, depends on whether we're using the white dipoles, the bigger ones in one side, or the smaller ones, which are painted red in the back. That's the versatility of the antenna. So the frequency range of the antenna is basically 5.8 megahertz up to 30 megahertz. We can use 2 dipoles, we can use 4 dipoles, we can use 8 dipoles, we can use all 16 of them. When we really have to put a narrow, like if we're going to the Arabic-speaking world, which is kind of on the other side, or if we're going to beam down to Australia or someplace like that, we'd probably use all 16 dipoles with a pretty narrow beam directed at a heading to get into that area. It's like an optical searchlight that we can change the beam focus whenever we want. The switching of dipoles is commanded here, via a computer, but the switching is done at the antenna in the tubular section. How many levels are there? What is it? There's like 7 levels.
7,
yeah.
And it's on what,
Right.
4?
Pardon? I think it's on 5 and 6.
Would those be
It's been a while.
solenoids that are closing?
They're big RF switches. They stand like yay high and wider than probably both of us. And they have these ceramic arms with these metal fingers on them. And they're run by electric motors and solenoids. So when they command to go to like a 4x4 configuration or a 2x2 or an 8x8, the switches will go and switch in, and these big arms will like switch over and hit into a pad to, because there's a lot of voltage and a lot of current at a 500,000 watts, and that's how we configure the antenna. And it's all done from the control room here, and everything is controlled by the Siemens controllers.
The antenna mast at WBCQ is secured to a concrete base 40 feet by 40 feet by 12 feet deep, which is anchored to the bedrock beneath it.
Incredibly rebarred, and that sits on top of ledge here,
And then, of course,
it will not move. Everything is grounded and strapped to and welded to the rebar cage, which is all welded together, and that forms the ground base for the antenna, mainly for lightning. But it doesn't use a ground screen per se like an AM transmitting antenna would use. It doesn't need it because it has its own reflector in the curtain reflector.
The 500,000 watt, $30+ million radio station was built from scratch, from the ground up. But Allan and Angela found at the beginning of the project that it was difficult to convince some of the vendors to take them seriously about the project.
Building a 500,000 watt shortwave transmitter with a fully rotatable antenna is no easy task. It takes a lot of planning and a lot of devotion and just a lot of dealing with all kinds of thousands and thousands of little issues. But that's really how we started. You pick up the phone and you go, hey, I need a 500 kilowatt transmitter. What can you do for us? Can you give us a quote? But it's interesting, though, that in the beginning, when we did that, we weren't taken seriously. It took several months before the vendors started to really consider that we were serious. Angela was in the construction business before we got married and together, and the attention given to people that want to do stuff, big stuff, was a lot better. I mean, I did find it a little strange that there was this kind of reluctance.
The main engine of the transmitter is a large water-cooled vacuum tube designed to convert 10,000 watts of input into 500,000 watts of output RF power.
The transmitter is actually, it's simple in concept, where you basically have a master oscillator, a frequency synthesizer, that goes into an IPA stage that boosts it up to a kilowatt, that goes to a vacuum tube driver that boosts it up to about 8 to 10 kilowatts, and then that goes into the Thales 176, type 176 tetrode, which is an output tube. It's about that high, about that wide, costs $210,000, is water cooled, and it will take 10 kilowatts in and basically give you 500,000 watts out. But the gain of the antenna, depending on the configuration, can boost it up to 20 million watts. And we do that so people that have a small, little, cheap shortwave radio can just pull out the little antenna, tune in 9330, and hear us.
The transmitter is cooled by a combination of circulating air and a closed-loop water system. The water cooling system is based on distilled water, which pulls excess heat from the transmitter to a heat exchanger. This water is constantly monitored for its electrical resistance, so it won't create an opportunity for any stray currents inside the transmitter system.
Everything's water cooled in it. The capacitors, the vacuum capacitors, the coils, all the tubes, the tube sockets, the mounts, everything is, the majority of the big RF components are water cooled, and then the rest of it is circulating air. And we distill our own water to opt up the system, because the cooling water for the transmitter is a totally closed loop system, and there are two. There's an outer loop that feeds the outside heat exchanger that has to have glycol in it because it gets so cold up here. And then there's the inner loop that has pure distilled water. They actually have both distilled water, but the outer loop has glycol. The inner loop has nothing but pure distilled water. And we monitor its conductivity. It has to be below, has to be so many, megohms of resistance to be able to use in the transmitter, so it doesn't conduct voltage or RF as it circulates through all the, to cool all the plates or the anodes of the big power tubes. So that's to top it off. Occasionally there are leaks. I mean, the transmitter has hundreds of little fittings and lines. It is really a plumber's nightmare. I mean, running BCQ, you have to be a computer person, you have to be an engineer, you have to be a mechanic, and you have to be a plumber. You need seriously, you need all these skills to be an engineer here at the World Superstation.
As can be imagined, a transmitter of this magnitude will present its own unique set of problems and challenges for engineers to troubleshoot out.
And we had all kinds of interesting problems with it when we first were firing up. What was the first problem?
The screen ring.
The screen ring, the leak. It's all water cooled, so the transmitter sprung a leak in the power amplifier stage when we were first testing and firing up. And it dribbled down the side of the tube and shorted out something known as a screen ring, because the tube has an accelerator voltage that works at around 700-800 volts. And it shorted that out. So we had to pull the tube out and clean all that and fix all that up and put that back.
Allan is an old-school radio electronics technician with many decades of experience in station design and operation. In one instance, he had to take the transmitter's designers to task to deal with an RF problem inside the transmitter that was causing component failure to occur.
Then there was a problem with the grid input circuit, which kept burning these bias resistors up. And I kept telling Continental that the design of the grid feed was wrong. It's interesting when you deal with a big company that's basically, and they build good stuff. I mean, Continental builds great equipment. Their equipment is well designed and good. In this particular instance, Angela knows, because of the frustration of all the emails that we sent them saying, no, your grid input circuitry is wrong. There's too many circulating parasitic currents there that are going to create heat and blow things up. And finally, without really agreeing, they changed the design. And they said, you're right, we need a choke here, we need a choke there. They redesigned it. We haven't had a problem since. It's simple in concept. The transmitter is complicated because it's controlled by Windows 10 operating system, Windows 10 operating system, which has its own issues. And everything's monitored. The transmitter is really well monitored for temperature, fluid flow, backward RF, VISWA, overloads. There are even little arc detectors in it, which were driving us crazy. Remember how they were driving us crazy? Because there was a crack in one of the doors, and the sunlight would hit it on a certain day and trip one of the arc sensors and dump the transmitter. So the fix for that was masking tape. So we did all kinds of little things like that. But finally, after a shakedown of about 6 months, we got it operating pretty smoothly.
The transmitter is powered by a 14,000-volt three-phase power supply. The local power company actually had to build a new three-phase infrastructure through the small town of Monticello to provide power to the new radio station. The transmitter is powered by a three-phase 14,000-volt audio-modulated power supply. The power supply is composed of multiple smaller power supply modules, which are connected to the audio feed via fiber optic cable. The power supply itself is what provides the amplitude modulation, as it is increased and decreased according to the audio frequency, which then modulates the 500,000 watt RF output tube to create the AM signal that puts the station on the air.
The power supply is an interesting situation. It's 14,000 volts, and it's all digitally controlled. Imagine a power supply with 48 800-volt little power supplies, and they're all connected by fiber optic to a computer. And the computer tells all those, and they're all wired in series. So the computer tells all those power supplies when to turn on and by how much, according to the audio modulation, the music and talk that goes into the computer. That's how the transmitter modulates the RF carrier signal in the air. Basically, it's a bunch of series power supplies controlled by a computer to go on and off at an audio rate. It's simple in concept, a bit complex in application. The superstation is kind of like on the level with, it really is like a power station, because we have, three-phase megawatts of power coming in from the local power company, and then we convert it to the final 14,000 volts to run the transmitter, and we have a huge electric bill, but it's worth it. It's a lot of fun.
The feed line that connects the transmitter output to the antenna array is a coaxial copper tube that runs from the transmitter out to the antenna array several hundred feet away from the transmitter facility. The outer portion of the feed line is a 9-inch diameter copper tube, which acts as the shield, surrounding a smaller 4-inch diameter copper tube that is the feed line's center conductor.
We have a 9-inch feed line. Imagine a copper pipe 9 inches in diameter, and then running through the center of it. How big is that center conductor? What is it? It takes about 4 inches. Yeah,
I was going to say.
Because it's 50 ohms. It's about a 4-inch center conductor.
It's been a while.
And it's known as a coaxial line. It's the same kind of coax that you would use like on a CB set to connect your antenna to your CB set, except it's 9 inches, and it has a rating of about, I think it can do about 1.5 million watts is what it can carry. The 9-inch outer copper pipe is the shield, and the 4-inch inner copper pipe is the actual center conductor that conducts the RF energy.
Center copper solid or just a tube?
It's a tube.
Okay.
Yeah.
So what's the dielectric? Is it just air?
The dielectric is air, meaning the insulating medium is air. The center conductor is held in the transmission line by these huge nylon rings, and then we pump dry air in it, desiccated air, no moisture, and that's the dielectric. That's what insulates it from one area to another.
The 50-ohm balanced line tubing is then connected to an antenna tuning unit inside the antenna mast. It feeds balanced line systems that then go through a series of RF switches and a rotating mechanism to allow the mast to rotate 360 degrees while maintaining an electrical connection to the dipoles.
The 9-inch line goes into the base of the antenna. It hits an elbow, so right angle elbow, and it goes straight up. The first place it goes is into an RF switch that enables us to do maintenance on the antenna. So we can switch from the transmission line to like test equipment at the antenna for tuning purposes. Then from the RF switch, it goes to a rotary joint. And the rotary joint is interesting because what it is, it's a piece of 9-inch line that's cut in, 2 areas? And it has all these metallic fingers. And it rotates because the antenna can rotate. And so it goes to this rotating section. And then above that, it goes to something called the ATU, the antenna tuning unit. And in the antenna tuning unit is a series of coils and vacuum capacitors that are all tuned by electric motors, and they have sensor, Celsin sensor sensors on them that tell the computer what position the vacuum capacitors and the coils are, because for every frequency and for every configuration of the antenna tuning unit is important to match the 50 ohms of the transmission line to the roughly 200, 300 ohm balanced lines that come out of the ATU and feed all the dipole arrays. So it's quite a mechanical marvel. I had engineers out there with test sets that feed signals into the antenna at very low power, like a watt, and they measure the reflected power back, and they can tune the antenna tuning unit and preset it for all the operating frequencies we may be using now and in the future. Currently now, the station is set for 9330 kilohertz, and we don't really have any plans to change frequency. We're kind of sticking with one frequency because the signal is heard so well around the world. We're trying to establish 9330 as the frequency for this WBCQ World's Last Chance station.
The studio for the superstation WBCQ features state-of-the-art digital sound cards, a digital mixing console, and PC-powered antenna rotating software. As a bit of nostalgia, there is an old Collins radio in the rack that is used to monitor the on-air signal of the station. Shortwave radio is a 100-plus-year-old technology which goes back to the early years of the 20th century, long before internet and cell phones have spoiled society with the instant gratification of news, data, and information at their fingertips in a split second.
To me, shortwave radio is vital. I mean, the internet is fragile, and we have listeners. Like just yesterday, we got an email from a listener way out in the willywags. Doesn't have internet, doesn't have a computer, doesn't want one. And he had an old vacuum tube shortwave radio in his basement. This is just yesterday. And he cracked it open and tuned it in, stuck a 1 meter piece of wire out the back of it, and tuned in one of our stations with all the crazy, wild programming that we have. And sent,
wasn't it harsh?
Sent us a text on his phone and said, "Look, I just tuned you in and we love it. Thank you for being there." And shortwave radio is something I think will always be with us. We get into the basements and attics of North Korea and the areas of the Arabic-speaking world where people don't have broadband access, but they have a $5 or $10 shortwave radio. That's why we broadcast. We broadcast 500,000 watts, but the gain of the antenna, depending on the configuration, can boost it up to 20 million watts. And we do that so people that have a small, little, cheap shortwave radio can just pull out the little antenna, tune in 9330, and hear us. And it's vital, and it's important.
And part of my opinion of it being eclectic is only because a lot of people don't realize it's out there. I'd like to see it more mainstream. Well, I'd actually like to see shortwave right in the cars.
Allan acknowledges that his wife, Angela, is a very valuable part of the WBCQ team.
I just want to take a personal moment because I have to thank my beloved wife, Angela, because constructing this, there were lots of trials and tribulations with everything from the contractors to the suppliers, and she's had a lot of experience in that business and helped us get through all that and do the negotiations and make the payments and keep everything on the up and up and keep everything everybody happy because it cost a lot of money to build this, a lot of good hard-earned money by very devoted people and us all to build this. So I gotta thank my partner here, my beloved wife on that.
Good job.
Yeah, good job. Yeah.
So,
She's very modest. She won't bring that up, but she really supported me during trying times with crazy people.
World's Last Chance Radio plans to produce more than 100 episodes that will be broadcast around the world in multiple languages from the superstation WBCQ. It is their earnest prayer that these messages prepare the listeners to stand faithful through the impending crisis of ages.